we consider smooth projective variety X over field F. And we consider the growth-ended ring, which is whose elements are classes of vector bundles over X. And Grothendieck invented so-called gamma filtration to approximate the topological filtration. Gamma filtration we denoted by gamma of X for the gamma filtration. If the degree is 1, then it's just kernel of rank homomorphism. And if I is bigger or equal to 2, then it's a subgroup generated by gamma operation. I'm sorry. Right. And xi is in the first gamma filtration, or xj. And the sum of these indices are bigger or equal to I. And the topological filtration we denoted by T I of X. Is generated by the structure shift of closed subvariety Y. Y is a closed subvariety of X of codimension bigger or equal to I. So we have the following filtration on Grothendieck ring. First, topological filtration. And the last one is 0. We have gamma filtration. And for the first two degrees, they are same. Gamma filtration and topological filtrations are same. And in general, it's known that topological filtration always contains the gamma filtration. And moreover, the over Q coefficient, then the topological filtration and gamma filtrations are same. And for the subsequent quotient of topological filtration, and Chow groups of codimension I. Chow groups is the algebraic cycles modulo the rational equivalence. And there is a group homomorphism induced by I's Chern class. by the Riemann-Roch theorem. Indeed, we, for any class of structural sheaf maps to some multiple of y, and codimension of y is exactly I. And again, by Riemann-Roch, there is a obvious surjection from Cho group to the topological filtration, which maps any class of subvariety to structural sheaf of closed subvariety and is surjective. And by Riemann-Roch, this surjection, the composition with P and P composition, the Chang class map, so just multiplication map. By some constant depending on I. So in particular, this means that over Q, Ci and P are both isomorphisms. So over tensor Q, there is no difference between gamma filtration, topological filtration, and Cho group. But over Z coefficient, the only difference between gamma filtration, topological filtration, and Cho group is torsion. And in particular for small degree, when I is 1, as the topological filtration and gamma filtrations are same, which is isomorphic to topological filtration. And which is the Picard group of X. When I is 2, the subsequent quotient of topological filtration is isomorphic to Cho group of codimension 2. And for some particular case, Grothendieck observed that when X is the base field is algebraically closed field, and X is the variety of Borel subgroup G mod B. In this case, Grothendieck showed that the associated graded ring of gamma filtration is torsion free if and only if G is of type AN or CN. So SLN or SP then. And Karapenko also studied the gamma filtration on the variety of Severi-Brouwer variety, which is a twisted form of projective space. Indeed, he used the following exact sequence. So and the corner of this is, and we have the following exact sequence, and this is equal to gamma 2. So and this exact sequence induces the following exact sequence. Torsion means torsion subgroup of given group, abelian group. Torsion subgroup of topological filtration. And this is indeed isomorphic to Cho group of codimension 2. So it's and Karpenko studied the case when X is the Severi-Brouwer variety associated with division algebra of exponent P. And he computed the torsion subgroup of Cho group of codimension 2, as well as the torsion of gamma filtration. And is a cyclic group of order P or 0, depending on the algebra. And recently, the Garibaldi and Jane Ulin also studied this sequence, and they showed that the torsion subgroup of gamma filtration is a cyclic group of order Dynkin index. So here, NG is the Dynkin index. I will explain this notion later. And here, in this case, the X is the complete flag. So now one may hope to compute the torsion of gamma filtration of higher degrees. So to do this, I will introduce some algebraic notions, and then we map this information using de Mazur's characteristic map to the gamma filtration and Cho groups. So now we consider lambda. This is just free abelian group. of finite rank with basis omega 1 to omega n. Then there are two augmentation maps. One is from the group link to Z. We denote by E epsilon m. We take so this augmentation map sends e to the lambda to just 1. And this kernel is denoted by I multiplicative augmentation ideal. And one can also consider the symmetric algebra, lambda, and there is a augmentation map. Any element of the symmetric algebra goes to 0. Any positive degree elements goes to 0. And this is denoted by the additive augmentation idea. Then there is a ring isomorphism between the quotient group ring to symmetric algebra. And we denote it by Pi. This map is defined by any element of group ring omega j to product of 1 minus omega j to the minus aj, and the inverse map is just defined by omega j goes to 1 minus e to the minus omega j. This is a ring isomorphism. Then we consider the composition map from the group ring to the quotient. To the i's component of symmetric algebra of degree I. And we simply denote by Vi. And for using generating functions, one can find the explicit expression of this map. For example, the phi of 1 is maps e to the lambda to lambda, where the lambda is just sum of omega j, and degree 2 extends to lambda square and plus the twisted form of lambda. Here lambda 2 is just square of this. And similarly, one can find the explicit map, this Pi. Now we consider the case when a finite group W acts on this free abelian group lambda. Then one can consider the W invariant augmentation ideas. The additive one, which is an idea of the group ring, which is generated by W invariant augmentation idea. Similarly, one has the additive W invariant augmentation idea. IA. Symmetric algebra on lambda. Now we define a so-called ice exponent of this finite group W. Which is just integer tau I is GCD of some integers ni, positive integers ni, satisfying ni times the degree I is contained in the image of multiplicative W invariant idea. So in general, there is no relation between these two guys. However, if we consider the case when W is a Weyl group and lambda is a Weyl lattice, then there exists this tau I. And lambda is just Weyl lattice. GCD of these integers, ni.
Is it a single integer, or is it a single one nano?
No, there are many ni's. GCD of all such ni's satisfying this relation. That gives the GCD. So tau I is the smallest ni satisfying this relation because it's GCD.
Ni is a set, or
Ni is an integer. I'm sorry. How can you take the GCD of sets?
so it's a set of numbers.
Yes, set of numbers.
Okay, what do you mean by multiplying ni to the idea?
Oh, this is a group, and you multiply some integer times contained in.
Ni is a set of integers.
No, ni is just single integer.
But when you fix I,
Yes.
what do you mean by tau I equals GCD of ni?
No, there are many ni's satisfying this relation.
Such that these 2 points means such that, right?
Oh,
I think it's one sentence, right? The definition of the Y.
Yes.
Right?
so it's ni is a collection of
Ye-
integers satisfying that condition.
Yes. Okay, okay, that's good. So it might be better to write, I don't know, ni's. Yes, for any fixed I, we have many ni's, so we take the GCD of all ni's. Okay, thank you.
So just for clarification, can I ask you something? So lambda is a free abelian group.
Yes.
And when you say Z of lambda, do you mean the group ring?
Yes,
or
group ring.
Not the polynomial ring kind of thing?
No,
And by
it's
the-
just group ring. Thank you. The symmetric algebra is a polynomial ring.
The number of variables is just
And indeed, from the definition of Phi, the Phi of 0, degree 0 element is zero. That means that the tau 0 is 1 from definition. And now we restrict it to a particular case when P is a loose system, a crystallography loose system. And W is a corresponding Weyl group. And lambda is a Weyl lattice. And in this case, it's known that there is no W invariant linear form. That means that the W invariant linear form is 0. And so W invariant with degree 1 is 0. That implies that tau 1 is 1 as well. And in general, by Shibali, this case the W invariant group ring is just isomorphic, is a polynomial ring in the character of fundamental representations. Here Vi is a fundamental representations. Oh, here we fix the rank of this loose system is n. On the other hand, the double invariant symmetric algebra is a polynomial ring in basic invariance, basic polynomial invariance. Over Q in this case. Qi is a basic invariance. For example, if the loose system is type of AN, then this basic invariance are just omega 1, the basis of Weyl lattice. Minus omega n to the I plus 1. This is just sum of e to the I plus 1. EI is a basis of the vector space, orthogonal basis. So this is over Q, but over Z coefficient, then one can find the generators, which is Q1 over 2 and Q2 for degree 3 are the generators of over Z. And one can find these integer coefficient generators. So now we can compute the tau i's in this case, because we have this description of a symmetric double invariant symmetric algebra and double invariant grouping. Before I state proposition, let me introduce another notion, which is Dynkin index. Sorry. And Dynkin introduced the Dynkin index of representation of Lie algebra G, which is just an integer J sub F, satisfying the trace of the image of this representation is a multiple of xy. Here, this parenthesis is a killing form on the Lie algebra, normalized killing form, which is normalized for any long root alpha is 2. Alpha is 2. And the Dynkin index of any Lie algebra G is the GCD of all such JF. And he computed the Dynkin index for any type. So it's a type of loose system. If type is AN, CN, this is Dynkin index, which is just 1, and which is either BN, DN, or the exceptional group G2 is 2, and F4 is 6, which is 12 of 6, I'm sorry. E7, E8 is 12 and 60. And it's already computed by Dynkin. And then one has the following proposition. And says the tau 2 is equal to the Dynkin index. And moreover, there exists tau 3 and tau 4, which divides the Dynkin index or tau 2. Now let me move to the application. we consider split simply connected group G. Over field F, and we fix a split maximal torus T. And we fix a Borel subgroup containing this torus. And we write X for the variety of Borel subgroup or complete flag. And lambda is just wave lattice. Or in this case, G is simply connected group, so which is just a character group of split torus. So, for example, if G is SLN, then T is the subgroup of diagonal matrices of determinant 1. And the Borel subgroup is subgroup of upper triangular matrices. Projective homogeneous variety G mod B is the complete flag, which is the sequence of vector spaces. Yeah. And now, by Dimazur, there are two characteristic maps from the group Ling and from symmetric algebra, which is denoted by multiplicative characteristic map. This comes from the group Ling to growth K of X, which sends any element to the associated line bundle L of lambda. And another characteristic map is denoted by C sub A, which is from the symmetric algebra to Cho group, sends any element to the Chang class of associated line bundle L lambda.
Substitute M and A for the multiplicative and the additive?
Yes, right. And by Steinberg, it's known that the K of X is generated by line bundles. It's well known that which is called Steinberg basis. The line bundles. we have a simple description of gamma filtration on the projective homogeneous variety. So it's just generated by product of dual of this is a dual of line bundle. And moreover, by Lima-Locke, the ice chunk class map sends this element. To -1 times and times the first chunk class of line bundles. Then using these facts, one has the following commutative diagram. Degree I, symmetric algebra, and we have a gamma filtration. And the chunk class map from the topological filtration induces this map. And the above map is just this number times the map phi of I. And these two maps are characteristic maps, multiplicative and additive. And this is commutative diagram. And it's well known that this Cho group of complete flag has no torsion because the Cho group is just generated by Schubert varieties, which is the closure by Brouet decomposition is just closure of this open set of G mod B. And this Schubert variety generate the Cho group of complete flag. So this guy has no torsion. And using this commutative diagram, one has the following theorem. For any I between 2 and 4, the torsion subgroup of gamma filtration is annihilated by let me write here. Sorry. Either 24 or the thinking index tau 2 times I minus 1 factorial. The above is if G is either type of Bn or Dn, and I is 4, and otherwise we use this tau 2 minus I minus 1 factorial. Indeed, the only torsion prime of groups of type Bn and Dn is 2. So in fact, this guy is annihilated by 8 groups.
Well, what is the role of this commutative diagram in that theorem?
So in the proof of the theorem, we use this commutative diagram. So for example, I don't remember exactly the proof, but so suppose we have a...
Correct the thinking index.
I'm sorry?
You use K to connect that problem with the thinking index.
Yes, because in the previous proposition, there exists tau 3 and tau 4, which divides the thinking index.
Yeah.
So we can use this tau 2 instead of tau 3 and tau 4. Yes. Because we don't know whether the tau 3 and tau 4 are less than the thinking index. So for the sake, we use the thinking index tau 2.
So here G is any group or
any simply connected group.
simply connected?
Yes.
And why this I is bounded by 4? Because it's very interesting phenomenon that normally higher codimension ones are very complicated, but I never saw any result that actually bounds like this.
Because we only computed tau I for any i's less or equal to 4.
So,
Because this can be extended to any I.
so that's actually for future projects? Or
Yes,
not,
right.
Not, okay.
Not right now.
This was
Yes.
so unnatural right now.
Yes.
Okay, I see. So you know this very small number of tau I, so that's why the theorem is...
Yes, we expected that the tau i's are all equal to the thinking index. Yeah. But we haven't proved this fact for a higher degree. Yeah. And let me finish this talk by mentioning some geometric application. So we consider the following exact sequence. Gamma I. So here gamma I means the gamma I of X. And of course is contained in topological filtration. And the co-kernel of this is tau I. So, and we write the E of some abelian group of M for the exponent of this abelian group of M. And the middle one, exponent of the middle one, divides the product of exponents of these two. And this guy divides the exponent of ti minus 1 and divided by gamma I, because this is contained in this group. This group is contained in this group, so exponent of subgroup divides the exponent of this group and times the exponent of same one. Now we can apply the above exact sequence recursively because we have the same form here. When I is I minus 1, then we have this. So we have exponent of this guy divides the product of exponent of gamma filtration. Let me use another index. J. And moreover, this exponent of ti quotient by ti plus 1 divides the exponent of this guy because there is a surjection from this to this. So using these two, and by Riemann-Roch, we have for any smooth projective variety y, we have this composition, and this composition is just multiplication mapped by minus 1 to the I minus 1 times I minus 1 factorial. So we have the information on the exponent of this middle one. So the torsion subgroup of so here is y is any smooth projective y. Is annihilated by this times I minus 1 factorial. Product of exponent of gamma filtrations. And together with the previous theorem, we have the following corollary. For i's between 2 and 4, the torsion subgroup of show group of twisted form of the variety of Borel subgroup is annihilated by we have very big number 2 to the 7 if I is 4 and G is Bn or Dn, and otherwise it's annihilated by I minus 1 factorial and product of J from 2 to I and tau 2 times J minus 1 factorial and otherwise. Here psi is the one cocycle, and this is a twisted form of the variety of Borel. For example, there is a one-to-one correspondence between the twisted form of variety and this cocycle. F is a base field and G is our group. Yes. The first cocycle. G. Yes. And it will be interesting if one compare this annihilator and with the torsion index. And Totaro completed the computation of torsion index of all groups of type Bn and Dn, and which is, and torsion index annihilates this Cho group, and that torsion index is 2 to the sum power, and this exponent depends on the rank of this group, but our result does not depend on the rank of our group. For any n, this 2 to the 7 annihilate the torsion subgroup of Cho groups. Thank you for listening.